Well, thank you, Anastasia, and thanks to that great introduction. It's a good time to mention that I now do training as well, so if you want me to come in and talk about all that stuff, then just let me know. But today we're going to talk about the special member functions in C++, the rules of 0 to 5 and beyond. So who here knows the rules of 0, 3, and 5? So that's about half, maybe just over. So there's a few of you that got a lot to learn here, which is great. For the rest of you, you came anyway. We're going to do like a recap from scratch on what they are and why we need them. And in my experience, even those of us that are very experienced have been following the rules of 3 and then 5 and then 0 is the best one, spoiler. For many years, we don't always do it right. We don't always do it all the time. Sometimes we need reminding why it's actually important to follow these rules and when. And what to do when we do need to fall back to, for example, the rule of 5. Getting that right is actually really tricky. And we'll actually get into a little bit about why as well. But then we will look a little bit beyond the rule of 0 even, times that we might actually need to consider things that don't conform to those rules and why. So let's get started then. I think the first one really just sort of sets the scene. This should be a surprise to nobody here. C++ is a complex language, and that's very often for historical reasons. There may be other reasons as well, but it's often the baggage that we've got from backwards compatibility with C, which is interesting because people who use C say they really like C because it's such a simpler language. Well, it is if you're only using C, but when you mix it with everything that C++ brings, all the high-level abstractions, the different ways of doing things, that's where the complexity really ramps up. And one of the main areas that this really comes out is in managing lifetimes of objects. One of the most fundamental things that we actually need to do in the language is also one of the most complex things because of this historical baggage. But we do have one thing in our favor. Well, sometimes this fights against us, but if we lean into it, we can use it to our advantage. And that's this realization that C++, like C before it, maybe even more so, is a value-based language by default. And we often think of managing lifetimes as being about, managing references, pointers, smart pointers, other resources. But if we always come back to this, that value-based language by default, and that sometimes that's where the complexity comes from, but if we can get back to the simplicity of that, we'll be in a good place. And that's really what these rules are about. Okay. Values themselves are simple when we get them right. Take the humble integer, for example. We're all familiar with how ints work, and that's the great thing about this. Right? We can initialize an integer with a value, and we might think of an integer as a value type. The value here is the 42. The integer itself, technically, is what we would call an object in the low-level sense. It's got a location in memory, maybe on the stack, but it's a location in memory. You can actually take the address of it, and there's a bit pattern there that represents the value 42. It is not itself the value, but it represents it. And it creates a really great illusion of being the value. The way you handle integers, unless you do start taking pointers or references to them, behave as if they are the values themselves. But we can also assign new values to that same object, that same thing in memory. And it will work just as you would expect. It's now got that new value. Great. Hopefully nothing is surprising yet. In fact, almost none of what I'm going to talk about in this session should be surprising, maybe a little bit towards the end. Spoiler, again. But this is what we want, no surprises. Now, we also have scopes for our values in C++, again, based on C. And if we consider that scope as well, we can actually, even with integers, consider 3 phases to their lifetime. There's the construction, where we give it an initial value. And we don't think of integers as having constructors, but again, if you look down at the low level, which is hidden here, and that's the great thing, but at the low level, initially, you've got a chunk of raw memory that is then initialized with that bit pattern and blessed to be the value 42. So that's the construction phase. We may then have an assignment phase where we give it a new value. Again, it's optional. And finally, again, not obvious necessarily, especially for an integer, we don't necessarily think about this, but there is a destruction phase. And all it's doing is that memory is handed back to maybe whatever's managing the stack frame, whatever. But you can no longer refer to that integer. And if you try, if you did have an outstanding reference or pointer, as we know, that can lead to a lot of problems. So we shouldn't do that. But if we just stick to the world of values, this is so simple, isn't it? I mean, the fact that I've just spent the last couple of minutes even talking about it seems maybe a bit over the top. Now, that's how simple this is. But if we talked about stood string instead, actually everything I just talked about pretty much still applies. We've got that construction phase. Now we've actually got a constructor that runs, gives it that initial value. We can reassign it a new value that works as expected. And there is a destruction phase. And an actual destructor runs, and there may be heap memory management involved, but that's all hidden from us. We never even get to see that. In fact, as we know, we should know, stood string is usually implemented with a small buffer optimization, so whether there's a heap allocation or it's all held within the object itself, that's all hidden. It's well encapsulated. We don't have to worry about it, usually. But when we stick to the world of values, this just behaves like a value type, exactly like the integer in this respect. Okay, so far so good. Let's do one more of these, because we can talk the same way about stood vector. Everything that I just said about stood string, apart from the small buffer optimization, applies to stood vector as well. It is a value type. It behaves like a value. When we assign things, when we copy things, they behave the same way. No surprises. This is what we want. Okay, maybe I've labored this point a little bit too much, but I want to introduce this book. Who's read this book, Effective C++? So that's less than half the room, maybe a third. Now, back in the early 2000s, this was required reading, effectively, for pretty much all developers. Everyone who's around at that time will have read this book at some point, or at least claim they've read it. And it's not read so much these days, which I think is a shame, because there's still a lot of really sound advice in here. Some of it's a bit dated. This came out to the peak of C++ 98 and then 03 days for the third edition. It was updated. Some of it gets updated, but most of it is still really sound advice. And I think we could do with rereading that sometimes. But there's one phrase that always sticks in my mind from this book, and maybe you've heard this one. I think it was coined in the first edition. Do as the ints do. So we just looked at string and vector, how they behave just like ints, at least with respect to the lifetime member functions. They behave as the ints do, and that's why there's no surprises. Now, he used this phrase in Effective C++. He actually said it again in the follow-up book, More Effective C++. And he was talking specifically about copy constructors at the time as well. But in that section where he talks about it, there's like 2 or 3 paragraphs of an absolute goldmine of quotes. Not all of them coined by Scott Mayers, but all very relevant. One of them, which I think is really important, adhere to the principle of least astonishment. So, another way of saying no surprises. This is what we want. Sounds boring, but it's great. Maybe a little bit more concrete. Recognize that anything somebody can do, they will do. They'll throw exceptions. They'll assign objects to themselves. They'll use objects before giving them values. done. I think he said a few other things as well, but these ones are particularly relevant to what we're going to be talking about. These things all matter, and they're all things we easily forget. So keep that in mind. But there's more. Just as a result, make your classes easy to use correctly and hard to use incorrectly. And again, he didn't coin this phrase, but I think Scott Mayles was instrumental in making this widely known amongst the C++ community. Make your classes easy to use correctly and hard to use incorrectly. Trouble is, that's often not easy to do itself because of that complexity we've talked about. But this is what we want to aim for. Oftentimes, the problem is we write these little throwaway classes, like for a particular purpose, and we think, okay, in this case, this is never going to be copied. It's never going to be in a situation where an exception is thrown. These things won't happen here, so I'm not going to bother with all those extra bits. Doesn't matter. And then, of course, one day something changes, and now it does. And it was never written that way in the first place. So if you're lucky, things will blow up. And if you're unlucky, they'll just be subtly wrong for a long period of time in production. And eventually, it'll catch up with you. So, as I say, tricky to get this stuff right. And we're going to go the long route in how you do make these things right. But then we're going to look at some shortcuts to get there, even with your throwaway classes. How can we make them at least hard to abuse so that you all know if one day somebody does use them in a way you hadn't anticipated. But let's go that long route first, and we're going to start just by bringing back this pattern, but now we're going to talk about pointers, because pointers are just values as well. So they actually behave the same way. Unfortunately, it doesn't often match the semantics that we want. And this is where some of the complexity comes from. But the pointers themselves, they're just values. C++ is a value-based language by default, so all of the defaults are geared up towards these value semantics. And if they're not the semantics we want, then we need to write them ourselves. So that's what I just said. All right, let's get into the meat of it. And while we've got these three phases, there's actually these, 7 member functions that we need to concern ourselves with, 4 different types of constructor, 2 different types of assignment operator, and the destructor. Now, none of these are, again, going to be new to you. I'm sure we write most or all of these all the time. That's not the point here. The point is, when you lay it out on one page like this, you start to realize, actually, there's quite a lot going on, and we have to keep in mind. Now, all but the custom constructor are what we call the special member functions. And they're special member functions because very often the compiler will write them for us if we don't write them ourselves. And then there's some other implications to that as well that we'll get into. The custom constructor. Interestingly, the custom constructor itself has an impact on the special member functions. We'll come back to that in a bit. It's this interplay, though, one it's trying to help, can often catch us out. So we'll look at that. But let's start right at the basics. Let's introduce a class. We'll call it gadget. Why not? Empty at the moment, but that's enough to get started. What we're going to do is, for each of these examples, we're going to gradually evolve. I'm going to show you the definition, some usage, and then as we'll see in a minute, what the output is, so we can reason it through. So empty class, we instantiate it, nothing going on, that's all fine. So let's make it more interesting. Give it a data member, so an integer. Nice simple integer. That's good. This all works, of course. We can even try to print out what that integer is. What do we actually get? Who knew it was going to be minus 2132? Forget the number. Obviously, it's a garbage value because we never actually initialize that integer. So there are some aspects of integers we don't necessarily want to copy. being so easy to leave uninitialized is not necessarily the best thing. Fortunately, we can actually deal with that. Before we do that, though, one little bit of practicality. I'm going to be showing lots of code, so to try to keep it condensed rather than having things like class and public, I'm just going to go with struct. But it's just simply for slideware, so try not to be too distracted by that. I'm going to leave lots of other things out as well, just so we can focus on what's essential. So same thing. All right, to initialize that integer, we could go the classic route, and we could introduce a default constructor, which explicitly initializes it to 0. And that's fine, and that works. Now the output is 0, as we can see. Again, no surprises so far. We could also initialize that in line with the default member initializer syntax, which we've had, I think, since C++11. So that's nice, we can do that now. There is a slight difference here, in that this is now initialized to 0 for all constructors that don't explicitly initialize it, whereas before it was only that one constructor. So sometimes it's not the appropriate option. So far, so good. But sometimes, in fact, very often, we don't want a default value. We always want a specific value. And the very presence of default values is another source of potential bugs that can make it hard to see because things sort of seem to work. They just don't quite have the values you expected. So if we wrote another constructor that takes an explicit integer now, and explicitly sets that, now we can construct our gadget with 42, and we print that out. We've got the 42 there, as expected. But having done that, having added this is a custom constructor, so that grayed out box from our list. If we try to default construct our gadget now, that doesn't work, which is probably what we wanted. We're saying we can now only construct this with an explicit integer. So this is nice, this is good, but it's something to be aware of, that by writing a custom constructor, we've inhibited the default constructor from being generated. It's one of the special member functions. That may be what we want. And that's true, of course, even if we did default initialize the integer in the body as well. Still can't default construct it. So this brings us to our first principle of the special member functions. In fact, two principles, really. First of all, that the compiler will generate special member functions for you where it can, where it feels it's appropriate, which may not be necessarily where you feel is appropriate. Fortunately, we can control that. But defining some of the special member functions, or in this case, a custom constructor, may delete or disable some of the others. I'm going to gloss over for the moment the difference between deleting and disabling. But the point is, in this case, we didn't get that default constructor. No problem. If we wanted it, well, we can write it ourselves explicitly. And we might do it this way, and this would work, at least if we've got that inline initializer. But, this is an example of an explicitly implemented default constructor, again. But actually, that's not necessarily what we want. This behaves the right way for now, but the recommended way to get back what the compiler would have generated, if it could have done, is to use equals default. Seems to do the same thing here, but not necessarily the case, particularly as your classes get a little bit more complex. There may be some differences there. And in particular, it will only generate this if it can. But you can here, but say you had a const member that you haven't initialized. It won't generate the default constructor, even though you've written equals default. So it's a little bit safer. So bear that in mind. All right, what about copies? If we create a new gadget and then copy it into our existing one using the copy assignment operator. Oops, jumped ahead. Well, so I've printed out the value from the copy. We've got our 42 there. We didn't write a copy constructor. It's another special member function that's been written for us by the compiler, which in this case does the right thing. Great. Okay, good so far. Compiler can do a lot of work for us. We should let it where we can. Okay, let's just add a chunk more code, all in one go. It's not terribly complicated. There's just a lot of it there. I'm going to do this now, because we're going to use this in the upcoming slides to help us to reason about the output. So in the constructor, we are writing to cout, and in the destructor as well, so we can see which one is which. And I've also got this global variable that we're incrementing to give us a what we're going to call a gadget number, so we know which instance we're dealing with. So we can see that in the output. I say not particularly complex, but I just want to give you a moment to make sure you've internalized that, because we're not going to see it again, but we're going to be using it. So a classic sort of RAII type that we might use. All right, let's change this up a bit. Oh, I should show you the output as well. And introduce a new class, struct in this case. This one's widget, of course. And now we've got 3 data members. Getting really complex now. So we've got a string, got an integer, and we've got a pointer to a gadget. These are all value types. And we've seen how they behave already. And straight away, we can print out their values. And just like before, of course, the integer, the pointer, uninitialized. So let's write a default constructor to give those some initial values. Seems like what we might want to do. Of course, that all works. But maybe we want some more interesting default values. So let's give the string a value. Let's give the integer something more interesting, and actually create a gadget on the heap. So far, so good. All looks good when we print it out. But actually, there is one problem. You can probably see, we're expecting this anyway, but we've got our gadget constructor being logged, but no destructor, because we've got new, but no delete. And you're probably all thinking, well, why are you using raw pointers? You know, we've got smart pointers. We solved this in the 90s. Yes, we did. We'll get there. But we need to see where this is going. If it helps, think of the pointer as just being a proxy for any sort of resource that we need to manage. It happens to be memory in this case. Okay. I'm just going to shuffle the slide about. This is the same code. Just give us a bit more room, because we're going to be adding more. Of course, we need to add a destructor, so we can delete our gadget. Great. Now we destroy the gadget. Everything's good. We're done. Or are we? What if we take a copy of the widget? Well, now it blows up, because now each copy's got a copy of the same pointer. They're both trying to delete it. So that doesn't work. Which means we're going to need to write a copy constructor. Okay, not too bad. We can just copy the name, copy the age, their value types, that's fine. But the pointer, that was the one that's giving us the problem. We can't just copy the pointer value. So we need to create a new one on the heap and invoke the copy constructor for that. Fair enough, no problem. That solves our problem for now. Until, instead of copy constructor, I should have pointed out that. If instead of the copy constructor, we use assignment, so you have to switch the order around there. We're back to the double deletion, because now again we are copying the pointer value, not the object. So let's try and add a copy assignment operator. And we'll follow the same pattern as the copy constructor, so we're assigning the string and the integer, creating a new gadget, assigning that. That looks fine. And it seems to work. Although if you look a bit closely, we're missing a destructor again. We've got a number 1, number 2, number 3. 2 and 3 destroyed, but not number 1, because, and you probably spotted it, but we are not deleting the old gadget, the original one that we had, before creating the new one, or before assigning the new one. Seems obvious, but it's also easy to miss, and won't necessarily catch us straight away. So, let's delete the previous gadget immediately before creating the new one, and I don't know if you can see that there, but it does actually delete gadget number 1 as well. Great, we're done. Unless an exception is thrown between that delete and creating the new one, either from gadgets constructor, which it could do, it's using cout, or the new, it's out of memory. So in that case, it's going to leave us now in a half-assigned state, where it's got a deleted gadget, but we haven't nulled out the pointer. That's going to blow up in the destructor. It's a pretty bad situation. So again, easy to miss, and it's probably not going to catch us for a long time. We can fix that by assigning our new gadget to a temporary variable first, then deleting the gadget, and then assigning the temporary. And now it all works. Okay, we're starting to get there. Until we try to assign to ourselves. We assign widget to widget. I mean, seems silly, but you can do it, and sometimes happens in generic code. So we should handle this. And actually, it seems to work. In fact, we got lucky here because we dealt with the exception. We're already holding our new value before deleting the old one. So what we've done is we just got an unnecessary copy. Maybe you can live with that. In other cases, this is going to be more catastrophic, so we need to detect self-assignment as well. No biggie, but another thing to remember. This is getting quite complicated at this point. But that works. All right, let's pause and just review what we've got here. We started out writing that destructor because we needed to delete that memory. And because we did that, we ended up having to write the copy constructor and the copy assignment operator. And it's actually quite a lot of code just for an empty class with 3 data members. This is all for the lifetime management of that pointer, really. The fact that we're having to even deal with name and age is only because we're having to deal with the pointer. We'll come back to that point. But this leads to what we call the rule of 3. If you're familiar with the rule of 3, this will be obvious. But, jumping ahead. The rule of 3 says, of these three special member functions, copy constructor, copy assignment operator, and destructor, if you have to write one of them, you probably have to write, or at least consider, all 3. And we've just seen that in practice. So, some of you may be thinking, okay, that's the rule of 3, that's outdated now. Now it's all about the rule of 5. And it is. We'll get to that. But actually there's still good reason to consider the rule of 3. I mean, it's simpler. It's a nice stepping stone to the rule of 5. And as we'll see, maybe this is all that's necessary sometimes. So remember the rule of 3. But let's come back to that assignment operator before we move on. I'm not quite done here yet. That was quite tricky to get right. Quite a few things we had to remember. Get the ordering right, self-assignment, new, delete, all going on there. Whereas the copy constructor was actually a lot simpler. So it's a shame that the copy assignment operator is so much more complex. It'd be nice if we could write one in terms of the other. And I'm old enough to remember when we used to have an explicit call to the destructor and then use placement new to construct in place within our own memory. But no, don't do that. Forget I said that. There is a better way, and you're probably familiar with this too, where we actually introduce a temporary, not a C++ temporary, but just a temporary variable that we construct. So that invokes the copy constructor, and then we just swap our members between ourselves and the temporary. So by the end, the temporary one goes out of scope, cleans up the resource, and we're in the right state. We didn't have to worry about self-assignment. We didn't have to worry about the ordering of when things get newed and deleted. We didn't even have to do the delete. So it's not just making use of the copy constructor, but also the destructor. So that's nice. It's slightly less code, but a lot less complex. A lot less things to remember here. This is pretty predictable. There is a bit of overhead. Maybe not so much in this particular case, but sometimes that overhead can mount up. We've got these additional swaps in here, instead of just assignments that we had before in many cases. Sometimes that matters. Most of the time it's fine, you can live with it. But for that overhead, as well as slight reduction in complexity, we also get what we call the strong exception guarantee. So now, if an exception is thrown at any point during the construction of the temporary, our state is unchanged. Our state only changes when we can fully commit, assuming that all of those swaps are no except. So that could be worth considering. Less complex, less code, stronger guarantee, slight overhead is the only penalty. So this is the so-called copy and swap idiom. One more thing to point out in here, you may have noticed the using std swap. I'm not just doing that because I'm lazy and don't want to type out the std each time. This is the idiom that we should be following now, because we have std swap, which the default implementation of which works pretty well for most types, certainly value types. We should use that where we can. But if you can write a more optimized version for your type, then if you use this idiom, that will be a better match than std swap. So you only have to just write swap for each one of these, and it will just pick up the most appropriate overload. So remember that trick if you do use swaps to implement your copy constructors, or for any other reason for that matter. So, okay. We could also take the widget by argument, the widget argument by value instead of by const ref, and that will save creating the temporary. Doesn't really amount to much different code in the end, just saves one line. Some people like to do that. I prefer this one because we're leaking less of the implementation into the interface, but that's a matter of taste. Okay, I think we're ready to move on from this. We're done with the rule of three for the moment. Let's see what happens if we introduce a std move. So we apply std move to our widget, and that now invokes a move constructor. So what happens when we do this? We haven't made any changes to the code, and it seems to work. Great. We didn't have to do anything. Except what it's actually done, of course, and you can see for the log, we've invoked the copy constructor. Because we haven't written a move constructor, it falls back to the copy constructor, which is nice if you don't actually need to optimize for moves. It will just work out of the box. Great. But if you do want it to move, well, we're going to have to write that. So let's have a stab at writing a move constructor. So take the widget by rValue reference, and let's try to move each of the members in. This is pretty much what we did before in the copy constructor, but we don't have to create a new one now because we're moving. That should work, shouldn't it? Obviously not. Got a double deletion again. The problem, of course, is because, well, you probably heard the phrase, std move doesn't move. And I'm sure most of us, if not all of us, know that, but it's easy to forget. When you see std move there, it just feels like it's actually doing something. It's not. It's just converting our L value pointer to an R value pointer. That's it. So the original value stays unchanged. We're going to need to explicitly null it out so that the outgoing, expiring object doesn't try to delete it in its destructor. Okay, straightforward enough. One extra line of code, no biggie. That's fine, that works. Whenever you see this pattern, though, of you move one value into another and then some other value into the original, sort of shuffle everything down one, consider using std exchange. Right, who regularly uses std exchange? A handful of people. It's not a huge life-changing feature, but it's just one of those little nice things that when you start using, you think, that's just that bit nicer. Right? It just does the same thing in one line, but it's also more expressive. Exchange is maybe not the best name. It's sort of shuffle everything down one. But yeah, look up std exchange if you've not been using it. It's quite nice. We've had it since C++ 14. 10 years now. It's about time. All right. One other thing we need to do with our move constructor, what we should do is make it no except. So move constructors should be no except if we can. And usually we can and we should. So unless you really, really can't, make it no except. And in fact, I would say again, if you can't make it no except, think about why. Can you change that? But why do we need to make them no except? Well, some operations will actually be overloaded on whether the type it's operating on are no except, or the constructor is, and will be optimized for that. And the classic example, of course, is std vector. If you put these objects into a std vector, if you don't have no except on there, even though you've got a move constructor, it won't use it, and it will copy things around. So that's going to be a big pessimization. Just for the price of putting that keyword there, you'll get move semantics in your std vector. So put no except on your move constructors by default. All right, that was move construction. What about move assignment? Again, same thing, seems to work, but it's doing a copy. Same principle. So let's have a stab at writing a move assignment operator. This one seems a bit simpler. So we can move the name, as in we can invoke std strings, move constructor. The integer, well, that's a copy, that's fine. And we can use std exchange again for the pointer. We could have done it longhand as well. That's fine as well. But std exchange, a little bit nicer. And of course, we made it no except. Interestingly, and I realized when I was going through these slides, I missed out self-assignment check. I don't have a slide for that. Just assume I've put that in as well. But even with that, this is actually a lot simpler than copy assignment. I think you'll agree. So that's not too bad. But with copy assignment, we also found that copy and swap was a useful idiom. Came with a little overhead, but reduced lines of code, reduced complexity. It was a lot nicer. And we've got the strong exception safety guarantee. Should we use the equivalent here, what you might call move and swap? You can, and it will work, but generally you shouldn't do that. Two reasons. One, as you can see, usually it's actually pretty straightforward already. Sometimes it can get more complicated than this, of course, but often it's a lot simpler. And secondly, that overhead starts to become a lot more significant when you're dealing with move operations. The overhead is actually additional moves. You're sort of doubling the cost of the call in a function whose main purpose is an optimization. So there's very little reason to use move and swap. You also already have, effectively, the strong exception safety guarantee here. If all of your moves are no except, shouldn't throw. So the move and move and swap idiom is not a thing. You've had to struggle to remember what it's called. So don't do that, but you can do this. Oh, and I should have shown the output as well. There we go. Okay, another recap. Now, by this point, I've got too much code to fit on one slide at a font size you can read. So I'm just summarizing with the definitions here, but we have now 5 special member functions, as well as the copy constructor, copy assignment operator, and destructor. We've introduced the move constructor, the move assignment operator, and we've had to implement all of them. Again, because of that destructor and the fact we now want move semantics, gives us the rule of 5. So we got there. If you implement one of these, you probably need to implement, or at least consider, all 5. Same reasoning. But remember, we didn't have to implement the last 2. If falling back to copy semantics was okay, rule of 3 still fine. So only opt into that extra work if you need to. Rule of 3 is still alive and kicking. But that was a lot of code. And even though this is fundamental stuff that everyone should know, easy to get bits wrong, forget details, think that's not important in this case, and then it turns out it was. We don't have to, who writes all that code for all of their types? I don't see any hands. Right, that says something. We don't want to write all that. Half the time it doesn't make sense. But the answer is staring at us right in the face. Like, if we just took out that pointer, then we're going back to a situation where, with no additional code, and I'm just going to put a little helper function to do the printing, we get all that stuff for free. Just works. Because integers, strings, they all do as the ints do. They have value semantics. And that composes. That's the principle here. If the only thing you have already implements the value semantics that you need, or the manager semantics that you need, we'll come on to that. That all composes, and you get that behavior for free. The compiler will generate all of those special member functions and give you the right semantics. It was only because we introduced that pointer. So if instead of introducing a raw pointer, we did what you all wanted to do in the first place, I'm sure, and use some existing type, it could be unique pointer, well, actually it doesn't quite get us there. Depends what you want. This won't give us the copy operations, but we'll at least get the move operations, and maybe that's all you need. That all works with no additional code. If you do need the copy operations as well, unfortunately then you're going to have to fall back to writing them yourself. Even with the unique pointer, slightly less code, and some of the complexities go away, but you'll still have to mention all of the values, which is unfortunate. And we don't have anything in the standard right now that's like a unique pointer but does copies. There's no copy pointer, unfortunately. There is a proposal for something very much like that, but at various times this has been 2 proposals. I think it's been rolled back into 1. This has been floating around for quite a few years now, hoping we'll get it in at some point, but indirect will be the one that we would use here. And that internally holds a heap allocated object by pointer, but will implement for you all of the copy and move operations and just invoke the right ones. Just what we seem to need. So I'm hoping we'll get somewhere with that at some point. In the meantime, there's a reference implementation on Jonathan Coe's GitHub at the bottom there. You can always grab that. Because as we sing, writing the stuff yourself, you can do it. It's tricky to get right. But this part does generalize. And so the principle here is make sure your class, or struct, whatever the type is, only contains things that are themselves value types, or, and I'm going to introduce this term, a manager type. So unique pointer is actually, it's a manager type. It doesn't have copy, so it's not strictly a value type. If you only had those things, we get the rule of 0, which, hope you all agree, is far superior. If you don't have to do any work and you get everything exactly right, you can't really beat that. So, always strive to have the compiler-generated special member functions do the right thing. And I put that in quotes because what the right thing is depends on what semantics you want. And if you're composing out of things that don't have the semantics you want, that's when you've got to do the extra work. So when that's the case, isolate the bits that don't have the semantics you want and write a wrapper just for those to give it the semantics. Because remember, when we were having to deal with that pointer, we had to deal with the integer and the string as well. Even though they did the right thing on their own, we had to deal with them all together. So wrap up just the things that have the mismatched semantics and deal with those separately. Use standard facilities or third-party libraries where you can, because it's hard to get this stuff right, even for experts. I even missed one of the things on my slide, the self-assignment check earlier, even though I'm giving a talk about it. So it's easy to miss. Writing your own managers, though, should be very rare. Most of the time, you can get the rule of 0 just pretty much out of the box, which is one of the reasons we've sort of stopped even thinking about it. It's like, oh yeah, it usually just works. But not always. We still have to think about it. All right. The title was the rules of 0, 3, and 5, and beyond. So we do just have a bit of time to go a little bit beyond. And I've already invoked the word manager. What do I really mean by that? Apologies for the slight blurriness here. I just copied this table from a blog post that I wrote a couple of years ago when I was working at Sonar. And I wanted to use the original rather than recreating it. So you can go read this blog post if you want more details. But I'd already spent a lot of time talking about value types and at least polymorphic base classes. There's also views, which we're not really going to talk about because they have different semantics altogether, but they factor in here as well. But then we get into these managers. We've got 3 types, and you'll recognize the pattern. Scoped managers, unique managers, and general managers. So scoped manager, the classic example is boost scoped pointer. Probably not very used today, because when we used to use scoped pointer, what we really wanted was unique pointer, but we didn't have it. But who's familiar with boost scoped pointer? Only a couple of people. Wow, okay. So it's like unique pointer, but doesn't do the move. It's literally just scoped within the immediate scope. You can't copy it or move it. Doesn't seem that useful, but actually it was, until we got unique pointer. If you do want move semantics, then you need a unique manager, and unique pointer is the poster child for that. But managers are more general than just pointers. And you can use unique pointer to manage non-pointer resources, and often that's the right thing to do. Because you can supply a custom destructor. Everything else should just work. Sometimes you need to write it more custom. So yesterday I was doing a workshop here on coroutines. Anyone that's used coroutines knows that there's a coroutine handle which doesn't have any sort of move or copy semantics. You have to build that yourself. And most talks and books and trainings that I see, they always just do it all in line with the other code, completely violating the rule of 0. So we actually did a bit at the end where we actually factored out a separate unique coro handle class, so we could follow the rule of 0. So that was a case of implementing our own unique manager. And general managers, they're the ones that also implement the copy operations, which really impart value semantics to a managed resource. And sometimes that's what you need to do. So indirect would be an example of that. Often you have to write it by hand. So they're the different categories of type semantics, if you like. And there's a handy list of when you might use these. But then there's which rules apply. So value types, the rule of 0 applies. But below that, it's generally the rule of 5. There's a couple of extra bits in there, which I'm going to get into in a minute. Then the fourth column, which special member functions are typically involved. So before I get into those extra bits, I want to introduce this table, which I also had in that blog post. Now, you may have seen Howard Hinant's version of this table. He's the one that really originally put this together. It's the intersection of, for each special member function that you write, what does the compiler do? And this is just my version of it, slightly different form. You have to sort of read it across. So if you look at one of the blue squares, you read across, you can see what effect that has on the other special member functions and the custom constructor. So when you see it laid out like that, first of all, the first impression is and should be, that's way too complicated. Why did we design this way? The fact is we didn't design it this way, it evolved this way. So the bits in red in the middle, so those red defaults. So if you define a destructor, you get a default implementation of the copy constructor and copy assignment operator. Right, that's what led us to the rule of 3. Because those defaults no longer work. You would think, well, actually, if we were designing this today, we'd say, well, as soon as you introduce the destructor or one of those other two, it should disable the others. We didn't make that mistake when we introduced move semantics, and that's why it looks different to the right. If you introduce either of the move operations, it disables the other move operations, if you haven't implemented them, and deletes the copy operations. Right, there's that difference between delete and disable. It never wrote the move operations. The copy operations, they exist, but they are deleted. Actually, we won't get into the subtleties of that. It is detectable. Point is, you don't get them, which means it's a lot safer. Unfortunately, we still have the legacy of the copy operations, and so we still have the rules of 3 and the rules of 5. There is one implication to this, though, which drops out of this. If you implement either of those move operations, those other special member functions are deleted or disabled, which is what we wanted. If you implement the move assignment operator specifically, if you see right over on the left, you get a defaulted default constructor, which is also generally what we want. Which means if you just write this, a deleted move assignment operator, that disables copy and move without disabling the copy default constructor. One line. There's a really nice shortcut. If you're just writing a little throwaway class and you don't want to have to deal with all the rest, you can just disable it with one line, which is not bad. The only downside to this is it's not very expressive. It doesn't actually say that that's what it's doing. It's a side effect of this mix of rules. It's sort of what we wanted, but because of the rest of the mess, we have to do it this way. So always write that comment as well if you're going to use this, just so you know what you're doing. And you're telling the next person, yes, I know, I haven't written those others, it's okay, they are deleted or disabled. But this is quite nice. And I didn't come up with this. I got this from Peter Summerlad. This is the lightning talk he did on it. He calls it the rule of Desdemova. And I can't remember exactly what that stands for now. It does relate to those operations. Watch the lightning talk, he'll explain it. Or he did a full talk, CPBCon or Meeting C++ 2021, what classes we design and how. So I didn't put the link for that one up, if you want full coverage. Really good talk, actually. Rule of Desdemona. Terrible name, great idea. So, coming back to this chart, you can see Desdemona in there. You can use that for the scoped managers, polymorphic base classes, to some extent even unique managers. This can cut down a bit on all of those operations you've got to write out. So the best shortcut is to follow the rule of 0. Second best is to follow the rule of Desdemona. And that has been mastering special member functions, rules of 0 to 5 and beyond. Thank you.